So first a warning. This is my personal view on everything, so you can be absolutely, do not agree with anything what I'm going to say. I'm not getting offended. It's absolutely normal. Variability has to be taken with a certain degree of, let's say, variability itself. Second, being very personal, it's only a choice of things that can be done. Yesterday, Dr. Klein told about the fact that not everything that is possible is worth being done, because in practice there's a number of different limitations that are not necessarily scientific or technical, that can be also economical. So just let's say, a view of different positions in the field. Now, let's see if this works. Okay, this gentleman probably you recognize, and his job has been mainly about variability, okay? Because variability is a very natural phenomenon. Variability is the common background to life. As we heard yesterday, no variability, no life, no evolution. Charles Darwin could stay home. Never had been what he is. So variability in reality is the founding concept of the evolution theory. Life itself is variability. There is no life without variability. As far as we understand life today, we all swim in a sea of variability. I like the idea of swimming because it gives you the idea of being able to move in any direction with minimal effort, and it gives the idea of the fact that you should try to move along with the current in a way, not to have the variability work against you, but work together with variability and trying to use variability for for the best. Okay, never put yourself against the current. Recognize that variability is there and do what you can do to go forward. So just a very tiny introduction to a typical, I would call it a typical but simplified feed flow. So we have ingredients. Each ingredient has its variation in its nutrients, okay? Then we add to that variation the sampling error. We add the analytical error. Then we have the data we use in our optimization. We take decision on this, but anyway, we get to a point where we have numbers that we use. Then we proportion the feed, and we have our rounding error in the diet. Then we proportion the feed, and we have dosing errors, scale errors, imprecisions, whatever you can think of. Then we have our mixing errors, because not every mixer is the same, and not every mixer is well maintained as it should be. Then you have, after you've made the mixer and you've pelletized and you've made everything, you have the segregation of the nutrients due to the different parts of processing, transport to farm and feeders, and finally, the errors of delivery that were mentioned yesterday. They are not at all something that does not happen. It happens. It happens, much more than we can think of. So there's a lot of points where we could say that there is a hot spot. To this, we have to add the fact that we are dealing with an area that uses words in a very specific way, that not necessarily is the way we use them in everyday life. So we are, especially when we are talking about sampling and analytics, but we talk about accuracy, we talk about error of measurement, we talk about random error, systematic error, trueness, bias, precision, repeatability, reproducibility. All these things have specific meanings in this context and slightly different meanings in everyday life. For example, this is the typical way we've been thinking about accuracy and precision, okay? Accuracy is just simply having the average value okay, but then if it's okay, you have a very high, let me see if I can run this thing. Yes, you have a very high accuracy because the average data is okay, but you have a very poor precision because the data is scattered around. This, the reverse, you're extremely precise because you're always doing the same thing, but you're doing it always wrong. So this is something you don't like. This is something you don't like very much at all. This is your target, but the bullseye is, well, it's difficult to attain. Seeing it from a different perspective, this is what we are looking into. So this is totally wrong for us. This is, well, accurate. It's not accurate, but it's precise. This is precise, no, but it's accurate, yes, because the average is okay. And this is what we have to look for. Said this, here we have a mix-up of different causes for these scattering of data around the average. There can be systematic errors and random errors. You cannot correct for random errors because by definition being random you cannot, but you can correct for systematic errors as far as you can find them. Very interesting if you can go and have a read of these materials from the Royal Chemical Society. They are excellent. They're excellent, let's say, very short and very concise things about ideas in terms of precision, analytical precision, but not only related to analytics. This, for example, is a different way to think what we've just seen. So it's not just a question of improving accuracy here means decreasing uncertainty, so reducing the error that is a systematic error built in the system. It's difficult for us to discriminate between all these errors within our process, the process I showed you before. So that's the approach we have. We are within the system of variability, and we have from within to deal with it. So you can see that definitely a different approach. So the problem that gets up, everything that is coming from here has been taken and re-elaborated from this paper here. I think it's a seminal paper, but it didn't give any follow-up, and it's a very, very good one. Very helpful in my professional life, anyway. So everything is depending on the goals you have. You're feeding the animals once, and then you'll forget it, and you go to a different business. You'll try to keep them alive. You're trying to produce consistently ingredients of the certain quantity. The more thing you ask, the more is different the level of variability you're going to accept, and the level of variability management you have to apply. Because what is the difference is the consistency. You want your results. So if we want consistent feeds, we have to deal with feed ingredients variability. So we have the real variability, as we said. Then we have all the problems related with the analytics, sampling, etc. And then the process, the feed processing variability. Variability in a feed is a complicated issue because the variability of a certain nutrient in a feed can be calculated in this way according to Faust. It's the sum, okay, of a number of compounds that are the product of the standard deviation of the nutrient in the feed mixture, each nutrient, okay, and multiplied by the fraction of the total nutrient contribution by the nth ingredients. That means corn has about, I don't know, to 15% of the variability of the old diet. So we multiply corn by the percent by its standard deviation. We square it, we sum everything, and we put it under square root. When you play with these things, results become unpredictable. They are not linear. You get results that can very easily go away. And what is interesting is that you can make a test about it. For example, you see here a list of ingredients. In the second column, you have the typical protein content for it. Then you have a percentage in a formulation, a very easy 3-ingredient formulation. You have the amount of nutrient that is delivered by each ingredient to that formulation for a total of 21.7%, that is considered to be 100. This is the protein percent coming from the different ingredients out of the 100. This is the coefficient of variation, i.e. the standard deviation in units, okay, nutrient units. And then you see that you have this value as the sum of all these ingredients multiplied. So it's the percentage of protein multiplied by 0.56. And then you have this number, you square it, and you get a coefficient of variation of 834 in this case. If we add an ingredient, and we add an ingredient that is not the best ingredient, it's probably one of the worst ingredients because it has the highest coefficient of variation. It has a 10 coefficient of variation, and we add a small amount of it. So one would think, but we are going to worsen the overall data. No. Due to the fact that we are working under square root, we are improving variability. We are reducing the variability. So protein variability goes away, gets lower due to the addition of another ingredient of the worst quality from the point of view of variability in that diet. Pretty weird, let's say, at least not something that we would expect. But that explains why traditionally we have been making diets with many ingredients. Because many ingredients even off the results. Even without knowing, we know that you use a little bit of this and a little bit of them, you will even out the result. But, so adding one more ingredient to your diet can decrease variability. Even if you are using an ingredient that is highly, highly variable. We saw this in the beginning of the year 2000 when we were deprived of the animal protein. And we went, it was very difficult to convince the feed millers in Italy that they needed to substitute the meat and bone with another ingredient. And so we simply reduced the nutrient with the ingredients, and we went to almost only soybean meal diet. And the result was that we saw an increased variability in our diets. All the nutrients increased their variability. And our results also a little bit suffered in the sense that the averages were good, but they were opened up, much more flatter distribution of results in technical terms in the field. The problem in using more ingredients or adding one ingredient to your list beside the practical side is, do you know your ingredient well enough? Because the problem is, are you having the same level of certainty about this new ingredient as you have for the other one you've been using? Because you cannot put things that you know perfectly together with things that you know nothing about. This is a very complicated issue because you should know at least what you're dealing with, not just put something in thinking that you know it, but having very little ideas about it. So yes, it can work, but your quality control, quality assurance system must be very adequate and must be able to give you the data you need. And are we sure that we are using our analytical capacities, the money we spend in controlling, in the right way? Are we spending them that's just to check the fact that we are controlling the ingredients that are creating most of the variation? Because that's the key. We must not spend money in things that are irrelevant to the variation. This is a long-standing battle. I once was running a feed mill lab, and my lab technicians were very clever, but they thought themselves as scientists. And so they were doing day-to-day controls, but they were thinking in terms of doing analysis for microelements, so how much molybdenum was in the ingredients or those kinds of things. And I had a very huge quarrel one day with them because I said, what I need from you is numbers that give me the chance to take a decision. I don't need numbers for knowledge. I need numbers for decision. Knowledge is good. I can use historical data. But when I use them once a year, I've used them. It's very difficult for me to put them to use every day. While I need everyday numbers to tell me that if I have to accept or reject that load. And that makes a very, very big difference in terms of your variability management. So, are we concentrating the word of our scarce, because they are always scarce, analytical control in the proper way? Because this is the very big question we have to make ourselves. Then, practically, do we have the place for a new ingredient? Have we got a bin? Well, yes and no, but depends. Let's say the advantage of one bin is so large that you probably can find it, and it's very depending on where you are in the world. For example, the next example I will make is much more practical than one would think, for example, under our condition in Italy, because normally we have very, very big scales, very long scales, and normally people in the feed mills have at least 2 bins for any large ingredient in order to dose them at the extreme of the scale to prevent the scale from creating problems of poor weighing. So, 2 practical ways to deal with the thing. One is overformulation, okay? So, you want 10, you ask 110. You can do it in 2 ways. One, surely increasing the nutritional concentration of the diet, and 2, discounting the ingredients, the key nutrients of the certain ingredients, by a percentage of the standard deviation. Well, the first one, I'd rather forget, because there is no way, it's apodictic. You cannot check it. Why? Why you decide for 3%, 5%, 7%, minus 10%, whatever. I mean, there's no control on it. It's just good sense, but it's very arbitrary. And how can you say that we are not over-formulating now? Because the problem is that if your reference is the standards of a breeding company, well, it depends where you are. What is the quality of the chicks you get? I mean, it's so... I'd rather think in terms of discounting, but discounting is expensive, of course, because you decrease the value of an ingredient, okay? But certain key ingredients, you do a decrease of their specific value in certain areas. It's also interesting because this gives you the chance of, in a way, be always within the low limits. Low asks you to be within a certain variation around what you declare on the label. So in this way, you're sure you're always, well, you have a higher probability of being within the label value you declare. Normally, what is applied is a minus 1/2 standard deviation out of the average you have, so that you can get to a point where you have about 67%, i.e. 2/3 of the samples that are better than what you expect. Of course, 1 standard deviation would be better. That would be a lot more than 80% of the samples, but that is going to be extremely expensive. But let's say that minus 1/2 standard deviation is pretty practiced. Let's put it this way. But then we take for granted that all ingredients are normally distributed. And their normal distribution is pretty unskewed and pretty symmetric. Are our ingredients really so normal? The problem is that I don't think so. This is a 2 years soybean meal. This is Argentinian soybean meal from an Italian feed compounder. So it's from January 1st, 2017 to December 31st, 2018, okay? This is protein, okay? And you see the variability. If we turn the thing the other way around, this is their distribution in terms of frequency at different protein levels, okay? And you see here indicated -1, -2 standard deviation. Please note that it's not very symmetrical. You have a much steeper side on this one and drops much more here. So the numerosity of samples in the -1 is much bigger than the numerosity in the +1 standard deviation. If we check another soybean meal, same company, this is Hi-Pro, Italian crush, 3 different oil mills. You see quite an interesting variability about these things. If we do the same rebuilding of the numbers, you see that here the structure is okay, 48 average, but here is completely the reverse. You have many more data points above the average than below the average in the high side. And of course here it's the reverse. So what does this mean? Well, this means that if you take let's say, a margin, and you reduce by half a standard deviation your value, the value you're using for soybean meal in general, and you apply it to this soybean meal and this soybean meal, so you get here or you get here, well, there's a substantial difference in the probability of overformulating. How much excess protein you will be making by using soybean meal. So in this case, you will not be you will be overformulating, but the amount of excess protein would be not so high. In this case, this is going to be definitely higher. And we also have problems in overformulation. We don't want so much excess nitrogen in our diets, especially in certain diets. So there's also the other side of the moon that we have to take into consideration. And it's difficult to put the two things together. So a more desirable approach, for example, would be to reduce ingredient variation by keeping the things separate, increasing the number of ingredients in a way, but in the sense that we are considering them different. Either we separate the same ingredient on nutrient content, we decide which is the key nutrient, and then we separate the ingredients. We have a break-even point where we decide above that it's product A, below that is product B, or by simple physical separation. We randomly throw the same ingredient in a number of bins, and then we pick the ingredient from the same amount from all these bins. What is the effect in practical life? Let's make this comparison of protein content in 5 different suppliers of soybean meal. So these are the 5 suppliers. This is data from Duncan in very, very old data. But anyway, it's not different. If you take these numbers, okay, each supplier has his own mean, his own standard deviation. Someone is better, someone is worse, okay? If we try and recombine the thing, okay, keeping them separate and not separate, meaning I check the protein and I put protein lower than the average in bin A and protein higher than the average in bin B, and then I take 50% out of each in doing the diet. Or I use them randomly. So with separation, with separation and without separation. You see that the standard deviation without separation is pretty substantial. It's calculated according to the equation I showed you before. And also the variability for lysine and for total sulfur in soybean meal and in the diet. And if you separate in terms of plus and minus the average, you see that you can drop your variability in the soybean meal by half, and the same in the diet. So it's definitely very interesting. It's a very good approach. It pays back. And whenever you can do it, you'd better do it. It's a very easy thing. especially today with NIR technology, if NIR would be used in the feed mill as a production tool and not in the lab as an analytical tool. And that is a very big problem in some areas, mine, for example, where the labs keep the NIR strictly as an analytical thing that it is not. And there's a lot of companies that are not really using NIR for its worth. That mainly for me would be this kind of thing. What does it mean? Okay, this is, you have to test soybean meal and decide if it's quality A or quality B. But what happens if, here, what happens if instead of doing this, we simply increase the number of bins? Okay, so if we do separation without checking, just simply putting the things, one truck in one bin, one truck in the other bin, we have a definite improvement, but it's only half of what we get if we do the analysis, if we do the control. If we have 4 random bins, we get to more or less the same level of variability than we have by checking the data. So it's a question of resources. Which kind of resources do you want to, can you spend? The NIR analysis or the bins? Have you got the bins? No use for analysis. Don't you have the bins? Use the analysis. But you can do something. The problem is that you have to recognize the need for you to do something. And that is the biggest problem. Then there's other things. And here we go on to very, very slimy area. Optimization tools. Yes, there's optimization tools. There are. You can do almost everything. They are not just the usual linear programming because they include the variability data for ingredients. So you need to have the variability data for each nutrient for each ingredient, or at least for the ingredients you want to control, and for the nutrient in the ingredients you want to control. You need to decide what is the probability of success you want, i.e. how many times out of 100 you want to be within the numbers you set as a requirement in your LP. And you have to know your analytical error data. Let's say that most of these things are totally unknown or very difficult to obtain, and very difficult to manage, and very difficult to maintain. Said this, that explains why the software has not been a big success. I can show you some idea of how it works. Here, you see this is an optimization screen. You see there's an area where it says standard deviations, probability deviations, analytical errors. This is the area where you add these numbers in order to be able to manage these things. So first, standard deviation. You have to put in the standard deviation for, in this case, I used just protein and energy, young chick energy, okay? This is variation in absolute terms. So it's 15 kilocalories, 15 kilocalories and 0.2, okay? So this is normal corn, let's say. And this is a highly variable corn for energy, a higher variable corn for energy. This is soybean meal with a higher variability for protein, okay? So I have 2 ingredients, one normal and one more variable for one of the nutrients. This can happen. Different suppliers can have different variabilities. Then you ask what is the probability you want to see. So I here said that I want to be sure at least 80% of the times that the result I get are within my limits for protein. But I accept that only 50% is for energy. 50% means that is not working. It's doing nothing, because normally when you're using averages, you are 50% above and 50% below. So asking 50 means if you put 50 everywhere, you have no optimization difference against your standard linear programming optimization. That will always give you data 50% above and 50% below. Then I set a specification, and a very, very simple specification where I put two nutrients, okay? Protein, from 18 to 20%. Energy from 3,000 to 3,100 kilocalories, with a target probability of 80 and 50, as I showed before. And this has been optimized at a certain cost that you see here in green, okay? So this diet here this is the screen that shows you all the probability data. The following one will show you ingredients. But anyway, this diet brings with it here. This diet brings with it 72% corn, 27.2 soybean meal, and that's it, okay? With these volumes, with these nutrients that you see here with where the arrows are. And this for a total cost, that is this one, okay? And we've been using the low variability product, okay? If we substitute the good variability product that you see here that you see up here, these are the good ones, with the bad ones, with the more variable ones, you see that the thing changes, okay? You see that the first one have been stopped as zeroed, so they don't use it. These are the different values. So we are using more variable ingredients, okay? And the result is more expensive. So the story is that whenever you do, you're adding limits. You're adding constraints. And these constraints cost money. But the problem is that it's extremely difficult for you to forecast what is going to be the money you're going to spend within this system. Yes? 5 minutes. OK. We're almost there. So you see tiny differences can give you interesting differences in monetary terms. But the problem is that it's extremely difficult to forecast what you are going to see. And I agree that we need a nonlinear approach to the problem. But the problem of a nonlinear approach is that it's not linear. So you cannot make prediction out of it. It's a black box. You put numbers in, rattle, and then you have numbers out. And then you change something that is in the 4th decimal of an ingredient, rattle, and you have something that's completely different. And you cannot make any projection of what you will be having. And that's hell for us. So optimization tools are available on the software market, but they need a thorough assessment of your data. Can you imagine some inconsistency that you can really skip in linear programming can create you havoc here? It's very complex to use and to put into use. And it's absolutely impossible. I said difficult, but it's an understatement. It's absolutely impossible to use in everyday life, in everyday optimization. Absolutely impossible. Unless you have a huge amount of resources delivered into it, because that's easy. OK, no problem. If you have unlimited resources, but we are not in a place or in a world where there's unlimited resources. Anyway, it is an excellent what-if tool, but you have to have money, time, and data. And data and time very often are the same thing. As we all know, data is the most valuable asset we have, okay? But it's not for free. The more data you have, the easier it is to control variation in an effective way, but data is costing you money, resources, and organization. It's very, very difficult. And from my point of view, variation in the nutrients in the feed is just one of the rings in the production chain, and my background as an integration nutritionist is clearly apparent here. So we have to be aware of the weakest ring in the chain, or the lowest stave in the barrel, because that is what first we have to meet. If we take a look again at the feed flow, and the thing we made here in green, you see all things that are the nutritionist problem, okay? Also the rounding error in a way. But all the rest is still having a huge impact, and it's out of our control. So I think that we need a much more systemic approach to variability in the production chain, not just nutrient variability management. It's just part of the problem. And we, of course, need to tackle it, but don't dare to think that you solve the problem, because you will never be able to solve it, and you will always have variation issues not coming from you. The feed has this big problem that is always the culprit because it's costing money. But one thing that we should try as hard as we can is to convince our people that, okay, we are responsible for cost, but we are not the cause of everything. Said that, you're all invited to the next ESPN in Italy in 2021 in Rimini. Thank you very much.